In this video, I am going to explain the DSC thermogram or DSC heat flow curve and how to use it to characterize the structure, phase and state changes of a material as well as chemical reactions in a material during a heating or cooling process. Please watch this video until the end and subscribe to our channel if you like this video. This will encourage me to develop such educational videos. Before understanding heat flow in a DSC, we need to understand the basic equation. Heat flow can be calculated as Q equal to mCp del T, where Q is the heat flow in watt, m is mass of a sample in gram, del T is the temperature difference in degree C. Considering the heat flow to the sample and reference, the equation can be written as Qs equal to Ms plus Mr times Cps times del T, Qr equal to Mr, Cpr and del T. Heat flow is commonly presented as watt per gram. Standardizing heat flow by mass of the sample could make the heat flow independent to the mass of the sample. To raise temperature at any level, Qs will be greater than Qr since mass of the sample and pan is higher compared to the blank reference pan. Therefore, we need to supply more heat. If a specific heat of a sample remains constant with increasing temperature, then we should have a horizontal line if we plot heat flow versus temperature. If a specific heat decreases with the increase of temperature, then we should have a linear line with an increasing slope, since more heat needs to be supplied. If the specific heat increases with the increase of temperature, then we should have a linear line with a decreasing slope. We need to keep in mind that the mass of the sample remains the same during the heating or cooling process. No heat generation or absorption in the sample, and a specific heat is linearly increased with temperature. Now we have completed a basic understanding of heat flow and its physical meaning as a function of temperature. Now I am explaining the basic characteristics of the heat flow curve and its physical meaning and their relations to the structure, phase and state changes of a sample as well as chemical reactions in a sample. That is, we can explore what is happening in the sample when it is heated or cooled. First, shift in the baseline. Second, exothermic peak. Third, endothermic peak. Fourth, exothermic peak after melting. Fifth, change in slope. In the following slides, I am going to explain each of the characteristics of the heat flow curve. If a sudden change in the specific heat occurs in the sample, then we will have a shift in the baseline, and a specific heat before and after remains nearly constant over temperature. The most common example is the glass transition. The glass transition is a second order transition since there is no latent heat involved and only a change of a specific heat occurs. In ideal cases, the shift should be at a constant temperature. However, in reality, glass transition occurs over a temperature. In this case, onset, mid and end of the glass transition temperatures are recorded. The change in del Cp at this transition is also estimated, and it indicates the characteristics and fraction of amorphous in the sample. Many characteristics changes show an exothermic and endothermic peak. Example of first exothermic peak is crystallization, condensation or chemical reactions in a sample. Example of second endothermic peak is melting, vaporization, gelatinization. An example of the third exothermic peak is cross-linking, that is curing. This could be a structure building in the sample. Most commonly, onset, peak, and end temperature are recorded to characterize the process. However, in some instances, maximum slope is recorded. Area under the peak is considered as the enthalpy in this process, that is joules per gram. At high temperature, a change in slope could occur. This could be reactions in the sample matrix due to degradation and oxidation. The change in slope also indicates heat is released with the structural changes and degradations. I have explained the DSC heat flow considering ideal scenarios. However, variations in real samples could occur. For example, the effect of heating rate on these transitions. In the next video, I will explain DSC heat flow curves considering food materials. I will consider few selected variations and their possible explanations. I would like to thank you for watching this video until the end. Please subscribe to our channel if you like this video.